Hey team, let's get cracking then. So you've got 3 lessons of pure each week, just until you come back into school. This first one is the first lesson about kind of further trigonometric functions, and this one's all about sec of x, cosec of x, and cot of x. Let me just change colour there because I don't want it to be in red. These are sometimes called the reciprocal functions. You'll have a little look at why they're sometimes called the reciprocal trigonometric functions, but mostly you'll just call them sec, cosec, and cot. Now, what are the reciprocal trigonometric functions? There are 3 of them, and they relate to the sine, cosine, and tan functions. Now, the first one is going to be cosec of x. Now, this one is related to 1 over sine of x. Okay, cosec of x is equal to 1 over sine of x. In other words, it's the reciprocal of sine of x, isn't it? Have a look. You see this third letter? It's an S. That's the one that's to do with sine, because that's an S as well. Okay, that helps us along. If we've got sec of x, well, sec of x, again, third letter is C. In this case, this is going to be 1 over cos of x. Again, that's just a reciprocal of cos x, isn't it? It's just the reciprocal. That is the exact same as cos of x, all raised to the power of -1. Okay? And then you've got cot x, which is equal to 1 over tan of x. Now, cot of x has got something also pretty interesting, which is because you know that tan of x is sine x over cos x. Cot of x is actually the same as cos of x over sine of x, and you use that pretty often with like tidying up questions, you know, simplifications and whatever else. There's a nice way of remembering that as well. COT, cos on top. COT, cos on top. There it is on top. Okay. Of course, you could have sine of x is equal to 1 over cosec of x. You know, these 2 things could be swapped around, but you don't tend to have to do that very often. So, are these just a fancy way of writing inverse sine? Now, remember from earlier on in school, you'll know that this is inverse sine, not with that bracket there. You've got sine to the -1 of x, okay, and use that for, you know, you might know an angle and then be able to try to find out like a side or something like that, or you might know 2 sides. You know 2 sides in a triangle, and you can use this to find out the angle. Well, this is not the same as 1 over sine of x. That is absolutely not the same. This is x applied to the inverse of sine. Okay, the inverse function of sine applied to x. This is 1 over the same function of sine just over x. The same function of sine applied to x. These are 2 different things. They're not the same. Okay, do not think that this is equal to this. That is not true. Okay, one of them is an inverse function, one of them is a standard function, but then it's got a 1 on top. Okay, they are not the same, so no. Okay. Use your calculator to work out these values. So nice and easy. Using your calculator, you've got sec of 280. So if we look at sec of 280, which one's this one? Is this to do with cos, sine, or tan? Have a little think. It's going to be 1 over something, isn't it? All right, well, remember, third letter rule. Third letter is C. And so this one's going to be cos of 280. Make sure your calculator is in degrees, and just tap that one into your calculator. Nice and easy. And it comes out, to 2 decimal places, we'll go with 5.76. Question B, we've got cot of 115. We should all know, I always just remembered it was because it was the T, but you're going to get 1 over tan of 115. Again, just tap that into your calculator, 1 divided by tan of 115. If you're not getting the same values as me, it's probably because your calculator is in radians. You need to sort yourself out. Negative 0.47 to 2 decimal places, 2 dp each. Okay, nice and easy. Next up, you've got work out the exact values. Now, work out the exact values implies that you're going to have things like surds and whatever else, but it also implies that you're going to have to use those magic trig triangles, okay? Your magic trig triangles being these ones, 1, 2, and root 3, with a 60 there, and with a 30 there. Okay, obviously that could also be called pi over 6, and that one could also be called pi over 3 in radian. And you've also got the other one, which is the equilateral, 1, 1, and root 2. So root 2, that is, I'm not very good at using this thing, and 45, 45, okay, where that is pi over 4 if you need it. Okay, work out the exact values. Normally in an exam you're going to have a calculator, so you just chuck it in your calculator, there should be no issues, but really this question is more about showing you that you can use these magic triangles. So we've got question A, sec of 210. Well, sec of 210, 210 is going to equal 1 over cos of 210. So we're going to need to find out the value of cos of 210, aren't we? Now, cast C, A, S, and T. And so you've got cos of 210, so you've got all the way around like that there, okay? Where that there is 30 degrees. We know it's going to be a negative. This is going to have to be a negative value, isn't it? Okay? And so what we're going to do is we're going to say, well, if I work out what happens if cos is 30 degrees, I can make that negative. Okay, these things don't go over 90, so I'm going to have to use this quadrant, aren't I? So sec of 210 is going to equal negative of 1 over cos of 30 degrees. And it's negative because this is a negative quadrant for cos. So it's also a negative quadrant for sec. They're the same quadrants. 1 over cos of 30, so that is the adjacent over the hypotenuse. So you've got root 3 over 2, so you've got negative of 1 divided by root 3 over 2. You can chuck that into your calculator if you want to, but you can also use keep switch flip, which is pretty nice for this, so you can go with negative 1 multiplied by 2 over root 3, which comes out as negative 2 over root 3. For B, pretty similar job, but you've just got radian, like it's not much more complicated. So if you've got cosec, well, cosec of 3 pi over 4 is going to equal 1 over, third letter rule is s, in this case this is sine of 3 pi over 4. Well, where's 3 pi over 4? 3/4 of pi. 3/4 of pi will be like that, won't it? Okay, which will mean that it's got a lot to do with what we would think of as being a quarter pi. You know, in other words, 45 degrees, some of you might think of it as. C, A, S, and T. Now, in this area here, sine is positive. In this area here, sine will also be positive. Everything's going to be positive there. And so, cosec of 3/4 pi is going to equal exactly 1 over sine of pi over 4. Okay, well, what's sine of pi over 4? Well, sine of pi over 4 is one of these ones, and so you've got the opposite over the hypotenuse. So that's 1 over root 2. So you've got 1 divided by 1 over root 2, which comes out to me as root 2. Okay? There'll be some more of these in the exercise that comes up later, but they're pretty useful to try out. But reminder that a lot of this stuff can go into your calculator. It might be a good idea to practice putting this into your calculator and see if it comes out with stuff like that. Okay, next, the graph of cosec x. So to think of the graph of cosec x, I'm going to start off by talking about this graph of sine of x. Now, we know that with the graph of sine of x, so we've got sine of x where this is x here, we know that something interesting happens we're going to go with 90 degrees here. We'll talk about the domains and the ranges in just a second, but we're going to go in degrees because it's the one I like. But obviously, you could think of this as being radians if you want to. Now, sine starts at 0, go up, down, down, and then up, okay, where you've got 1 there, and you've got negative 1 there. So that's the graph of sine of x. Now if you think about the graph of 1 over sine of x, this is what we're trying to work out when we're talking about cosec of x. Now what's 1 over each of these values? That's what we're going to have a little play around with. Oops, I don't know what I've done here. Well, that's what we're going to have a little play around with. So what is 1 over each of these values? I've never used that button before in my life. So 1 over 0. Well, when When sine is 0, you've got 1 over 0, and 1 over 0 is obviously just going to form an asymptote, isn't it? Okay, it's going to be undefined at that point. So we'll get asymptotes here, which is pretty weird because we were used to tan, it's asymptotes, but now apparently something that's related to sine is going to give us some asymptotes, and that'll happen whenever we've got a 0. Happen then. It will happen then. It will happen then. Now here, when we've got 90 degrees and then 1, or you've got you've got pi over 2 and then 1. 1 over 1 is 1. 1 over 1 is 1, and so therefore that will be a point that we'll be using. And when we've got negative 1, 1 over negative 1, it's negative 1. Now what actually happens is this graph goes really steep up, and you'd be tempted to think it's a bit like a quadratic, but obviously it looks a bit like it, but it does not touch these asymptotes, and so you've got to be really, really careful with that. Okay, don't try to draw a quadratic and end up with something that looks like that. It's just trash. Okay, that's absolutely rubbish. This graph here, this one, that's the cosec graph. The cosec graph is in that colour. Now, what's its domain? So the domain, remember domain, in. Which values can you chuck in? Well, you can chuck in absolutely anything, apart from x cannot be equal to, well, it can't be equal to 0, it can't be equal to 180, it can't be equal to 360, it can't be equal to any other, chunk of 180 after that, so it can't be 540, it can't be 720 or whatever else, because when you chuck those things in, you get a reciprocal, okay? So x can be absolutely anything apart from those, okay? So x exists within the real numbers except for those. For the range, now there are two separate regions for your range. You've got one that goes up like that and one that goes down like that, and so you've got, if we call this f of x equals cosec x, well, you've got f of x has got to be greater or equal to 1, or f of x has got to be less than or equal to 1. And of course you could use set notation for that and whatever else, you can use that U-shaped set notation if you're ever asked to. But there's your domain and your range for it. Now cosec is really, really similar to sec. I'm not going to do sec for you, you can just do it yourselves. It's not overly complicated, it's just a shift along. It's pretty simple. For cot, starting off with tan of x, again something interesting is going to happen every 90 degrees, where with tan it goes off up like that, doesn't it, and it hits, well, it doesn't hit the reciprocal, but it does have a reciprocal, it goes like that, there you go. So there's tan. Okay, now with that we've also got cot. Now cot of x is 1 over tan of x, don't forget that. So cot of x is equal to 1 over tan of x. Okay, so what's 1 over 0? Well, 1 over 0, we know that's going to form a reciprocal. Okay, well, 1 over 0, that's going to be a reciprocal there. 1 over 0, that's going to be a reciprocal there. 1 over something extremely large. Now 1 over a reciprocal is a bit weird, because if you've got 1 over 0 equals a reciprocal, well, 1 over a reciprocal must equal 0. It's a bit strange, but you should be able to spot that there will be one of the places where your cot wave is going to be attached. In actual fact, what it ends up looking like is a bit like that. There's my cot wave, that's what that one looks like. So it looks pretty similar to the tan wave, just obviously it's got like some differences that are in there. It's within each of these 90 degrees, it's sort of symmetrical around the 45 and the 135. So next up, example 4. Sketch the graph of y equals 4 of cosec x equals negative pi. 4 of cosec x, where x is between negative pi and pi. Obviously that there implies that we're dealing with radians. Okay, so the first thing to do would probably be to have a little sketch of what we think 4 of sine of x would be. we're used to that. We sort of know how that thing works. Now, 4 of sine of x, again, I'm just going to chuck in everything interesting happens every pi over 2 in this case. Well, sine of x goes up like that, okay, and like that there, okay, where that is 4 and that is negative 4. So just be really careful with that, because that peak there is going to be important over here in just a second, where that's 4 and that's negative 4. Now, when this thing is 0, we're going to get a reciprocal here. And here, we get a reciprocal there. So that's another, not a reciprocal, an asymptote, pardon me. You're going to get an asymptote at each of those values wherever sine of x was equal to 0. And then you get these sort of pinpoints. You see these bits where it goes up to 4. Well, it's going to go there. Okay, that is going to happen. And that one there is going to happen as well. And so you're going to end up with this thing here, off up like that, okay? And again, off up like that. Don't kind of sweat it too much about how you draw these things, whether that's exactly the same as that. Don't worry too much about that. Just make sure it doesn't cross your asymptotes. Now, bear in mind that here, this will be pi, and so this here will be pi over 2. Okay, here will be pi over 2, and here will be pi. Now pi is, we'll go with roughly equal to 3.14-ish, and so therefore this will be roughly equal to 1.57. It's a good idea to try to keep that in your mind. That'll be negative obviously, and that'll be negative, and so you get roughly equal to negative 3.14 and roughly equal to negative 1.57. Now, we're being asked, on the same axes, sketch the line y equals x. Now, y equals x is going to guaranteed go through there. I'll change colour actually, why not? It's going to guaranteed go through the origin, but also it's got some other stuff that it's guaranteed to do. Okay, well at 1.57 across, it's going to also be 1.57 up. It'll be something like that, okay, it'll be pi over 2 up. So it's going to go like that, guaranteed, okay, and it will also do the same over there as well, okay. That point there, for example, being pi over 2, because y equals x in this case. In actual fact, this line will carry on like that. Okay, well, eventually it will hit cosec of x, 4 cosec of x, but it won't do it in here. That's what I've got drawn. I carried on drawing this for absolutely ages, so it hit it loads and loads and loads of times, but it won't do it in there. These two things will never be equal to each other. Now, with question C, it says state the number of solutions to this. Now, this is not the same as what you've drawn. It's not the same as that. So, if y equals 4 cosec of x, and y is also equal to x, then 4 cosec of x is equal to x wherever these two lines cross. Both of those equations will be true whenever those lines cross, and so therefore wherever those two lines cross will indicate a solution, but those two lines don't cross, and so therefore the amount of solutions that you've got are 0. Next, sketching the interval, this thing. The reason I put this on, I think it's really important to do this, is that you need to be used to drawing things where you've got sec of 2 theta. It's pretty important. And you've also got this transformation happening as well. Now, between 0 and 360, you've got sec of 2 theta. So y equals, well, third letter rule is c, so you've got cos of x. Well, cos of x in between there would be a little bit better than this one, hopefully, but you've got one that looks a bit like that there, which means that sec will go off like that. We'll have a reciprocal. Reciprocal will go like that there, and also down like that. Okay, so sec of 2 theta, what does y equals sec of 2 theta look like? Well, 2 theta, that's happening kind of inside, isn't it? And what we say is that if this thing says multiply by 2, it actually means that we need to halve things, don't we? And so what we're going to have is going to be kind of rather than it being 90 degrees, or pi over 2 in this case, I'll use it's 90 degrees because we're in radian mode. We're going to have a bit of messing around to do with this, unfortunately. So instead of it being there, the reciprocal is going to be there. Things are going to happen a lot faster in this case, where that's 1. A lot sooner this little stuff will happen. Here, where you'd normally have this kind of sad face little curve between 2 notches, it's just going to be the width of 1 notch. Okay, so really, really closing in this stuff will do. Okay, where that there is -1. And once you've got a few of them drawn, you should really be able to sort of see how the pattern's going to go. And you'll end up with this here, with this here, and you'll end up with this here. Okay. Next, you've got 1 plus. Now, when you're thinking of 1 plus, I suggest thinking of it as being sec of 2 theta and then +1 on the end of it. Okay, so raise this whole thing up by 1, and so what you'll actually end up is something really, really similar, except you'll have 2 and 0 being kind of these shapes here. You should be able to sort of draw that yourself, but I'll do it for you. Okay, so we'll go up like that, go like there, there, touching, and there. Okay. So next up, we've got sketch the graphs of 1 plus 2 sec theta in the interval of this thing. Now this is one of the questions from the actual exercise, which I thought was well worth us having a little look at. It's a really weird domain for this, because it's -pi or to 2 pi, and it's not symmetrical, which is a bit strange. Write down the theta coordinates at which the gradient is 0. Now, gradient of 0 is obviously going to either be something that looks a bit like that, or it's going to be something that looks a bit like that. And deduce maximum and minimum values of 1 over. Now, that's really important. You see that this is 1 over this. So we're going to mess around with this, find this thing out, and then use 1 over it, which is a bit interesting. And it seems like that should be quite easy, but it's actually worth 4 marks, and so it's obviously going to be pretty tricky. So the first thing is that we're going to try to sketch the graph of y equals 2 sec theta plus 1. Remember on the previous example I said it's always easier to just put the +1 on the end. So first up, let's have a little look at cos theta between -pi and 2 pi. So we've got a cos theta between -pi and 2 pi. So we've got this thing here. So we've got there as -pi, we've got there as 2 pi. And so cos theta would start up there at 1 and down there at -1. But obviously we'll be messing around with that in just a minute anyway. So let's start off with there, 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 and there. We've got there and there. Okay. Next. So if that's what cos theta looks like, let's find out what sec theta looks like. I'm going to do 2 sec theta as well. Now 2 sec theta is going to be very much the same as this, except it's going to have 2 and -2. So we will have there. Always draw your notches on, it's a good idea, just helps you along. We've got a reciprocal wherever there's an asymptote, pardon me, wherever there is a 0. So fit those things in first, they always help you along. There's your asymptote. Now up at 2, we've got 2, and we've got -2. Those will be kind of where it pins on. Okay, and so we'll end up with there, and there, and there, and there. Okay. Now +1 is going to go up by 1. When you're doing that, I'm just going to change that to be a -1. I'm going to change that to be a 3, just to make things a little bit quicker. So it says write down the theta coordinates at which the gradient is 0 So which the gradient is 0 is going to be there, 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 and there. Be careful here, it's got or equals to, and so therefore these two things will be used as well. So for B, the values will be, well, if that's my axis there, I've got negative pi. I've got 0. I've got pi over 2 pi and 2 pi, which is that one there. And for C, deduce the maximum and minimum values of blah 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 and give the smallest positive values. Be careful, you've got to read every single word, so I'm only talking about this point here is going to be useful and this point here is going to be useful. Now the maximum and minimum thing for 1 over this graph, 1 over this graph, you might be thinking that you could use some sort of cos thing and whatever else on it, but it'd just be pointless. It'd be really, really, really difficult to do. So you've got, if I plugged in something very small, 1 over negative 1, that would equal negative 1. Okay, that there is actually the original graph, and we've got this new version. We've got 1 over, this is our turning point here, which is negative 1. I'm going to try the same on the other one, which is 1 over 3, which is that one there. In actual fact there, that is the maximum. You could try putting in bigger values, 1 over say 5 for example, where 1 over 5 is less than that. Okay, so that would be the most that you can possibly get. 1 over some negative value, well 1 over some negative value is going to be negative. These are all going to be lower than 1/3 but still positive, and these are all going to be negative, so that's our maximum there. And that occurs when theta is equal to 2 pi. That's the first time that it occurs. You might think it's that one, but that's not positive. It's 0. That one is. Here, this is the minimum. And that occurs when theta is equal to pi, which is that one there. Okay, your tasks, pause the video so that you can remember to do these. You're going to take a picture of them, upload the picture to Google Classroom, and I will be able to answer any questions that you have. You can get in contact with me and I'll try to answer them as best as I possibly can, but hopefully this will keep you nice and busy for lesson 1. Thanks very much.